Okay, so we'll continue. So what happened earlier is that um, this pathway, the formation of the carbocation is just not occur, no, because of course this one is much less stable than the 3 degree carbocation that we form here in the first. So the major product actually that we get here is this one, rather than this 2-bromo 2-methylpropane. So again, it follows the Markovnikov's rule: the rich gets richer and the poor gets poorer. It's important that you know how to write on the mechanism of the reaction, just in case you get lost or you get stuck. I always have to see which pathway will produce a more stable carbocation. So the general statement of Markovnikov's rule: in the addition of an asymmetrical reagent to a double bond, the positive portion of the adding reagent attach itself to a carbon atom of the double bond so as to yield a more stable carbocation. So this is what we have already understood this one. And the addition of electrophile determines the overall orientation of the addition because it occurs first before the addition of the nucleophile portion of the adding reagent. Okay, so this one, for example, you have this is our nucleophile, this is our electrophile. There is actually two portions here. The other first one is an electrophile, the other one is the nucleophile. So for example, you have your ICL, and you don't know which one is an electrophile or the nucleophile. You have to think which one is the more electronegative atom. So between iodine and chlorine, okay, chlorine is a more electronegative atom. So the electron density between these two atoms here will go to the chlorine. So chlorine will be partially negative and the iodine will become partially positive. So for example, if you have an alkene, it will add to here. Okay, it will add to iodine rather than chlorine because this is the one that is the electrophile and not the chlorine here. Okay, so and then you'll see where will it add? Will it add? Always have to think of a more stable carbocation. So if carbon will add to iodine, CH2 will add to iodine, okay, this second carbon will become the carbocation. If it's the other way, this one adds to iodine, then this one will become the carbocation. So 1 degree. So we'll choose the more stable carbocation, this pathway where we see a 3-degree carbocation. So once you form your carbocation, the liberated chlorine, once this carbon, CH carbon iodine is formed, okay? Pag ma-form na ng carbon iodine, the electrons gikan aning duha will go to chlorine. Okay, and you'll get your chloride. 2, 4, 6. Ika-8, katong gikan sa bond. Okay, so once you have your carbocation, this one will attack this carbon, and you get your alkyl halide. Okay, so what we'll have, give the structure and the name, the product that would be obtained from the ionic addition of IBr to propane. Give the structure and the name of the product that we obtained from the ionic addition of IBr to propane. This one is ICL. And we use the IBR. So again, you will have to think for IBR, which one will be more electronegative than the other halogen, and follow always the carbocation. So you can also practice 8.2, write the mechanism for this. A, B, and C. So I will give this the problem set to you. Provide the mechanistic explanation for the following. So show me the pathway of how you get this. Now you get this using this one, or this using this. So that will be an assignment. So just have to say that there is what we call as regioselective reactions. Chemist describes reactions, the Markovnikov's addition of hydrogen halide to alkynes as being regioselective. So regioselective comes from the word regio, which means regionem, or meaning direction. So a regioselective reaction is one that can potentially yield 2 or more constitutional isomers, but that actually produce only one. Okay, so for example, in the case of for example, no, so let's say this one, when we add the alkane to this hydrogen halide here, there's actually 1, 2, 3, 4. 5, 1, 2, 3, 4, 5. There's actually 2 possible constitutional isomers that can be obtained, but we will prefer one over the other, so we don't know which one of that. So if we know which one will be preferred over the other, which one will be more prominent than the other, then we call that one as a regioselective reaction. So the Markovnikov's addition that we have learned earlier is an example actually of a regioselective reaction. So the addition of HX of hydrogen halide to an unsymmetrical alkene such as the propene, as we have discussed, could conceivably actually yield to constitutional isomers, but we have learned that following the Markovnikov's rule, there is only one that is preferred in a higher amount, that's being produced in a higher amount. And because of that, the addition of hydrogen halide to alkene is a regioselective reaction that follows Markovnikov's rule. Sometimes it's also possible that a reaction can not follow the Markovnikov's addition. For example, here you have your CH3, CH double bond, CH2, and you have your HBr in the presence of a peroxide, ROR. This is just an R, another alkyl in any alkyl group. So in Markovnikov's rule, no, the rich gets richer, the poor gets poorer, or the carbon that contains the hydrogen, that's where the hydrogen will be added. So supposedly you have your CH3 and you have your Br here. But what you see here is that baliktad, no? See, hydrogen is added during a carbon, the poorer carbon, and this one gets the bromine. So it doesn't follow the Markovnikov's rule. So this one is what we call as the anti-Markovnikov addition. And this happens when there is the presence of peroxides like this. Peroxide kanang na mga ROO, kanang oxides, peroxide, like O2 minus. Okay, this one. Duha ka oxygen nagtapa, those are peroxides, and we'll see more of this when you go to chapter 10. Just know that once you have another agent added, like the peroxide, no, it behaves, it's what we call as an anti-Markovnikov addition. It doesn't follow the Markovnikov's rule. So consider, for example, the following addition of HX to our butene, 1-butene. And you notice that when we add here, the rich, if we follow the Markovnikov's rule here, the carbon containing the higher number of hydrogen will add 2 hydrogen here. So you have your CH3, and the second carbon from the double bond will get the X. Okay, and you notice that this carbon in the asterisk actually is an chiral center, is a stereocenter. No, this carbon is bonded to 4 different group of atoms. Okay, carbon, you have hydrogen, CH2, CH3, CH3, and halogen here. So once the halide is being added to, diba, when we add this one, you get actually a carbocation in this case. So the halide actually can add up and below. Katong hagaling na anapin up and below sa katong plane sa carbocation. So once you form that one, there's actually 2 possible pair of enantiomers that can arise. Okay, from that particular carbocation. And the product therefore can exist as a pair of enantiomers. So you will have, the question now arises as to how these enantiomers are formed. Is one enantiomer formed in greater amount than the other? Okay, so remember that once you form a carbocation, there are 2 ways that your halide can add up and below the plane. So the answer is a carbocation that is formed in the first step of the addition. It's trigonal planar and is achiral. And so when the halide reacts to the achiral carbocation, the reaction is equally likely at either phase. So it can act, let's go back here. Okay, let's say you have here carbocation. No? So this one is planar. Once you have your halide added to your carbocation, it can add up sa ibabaw aning carbocation or sa ilalom ani niya. Okay, because remember this is planar. So there's 2 ways actually that your halide can add up and below. And the probability that it can add up and below, up or below, is actually equal in such a way that we will produce, the reaction is equally likely at either phase from the achiral carbocation. And because of that, what we will get is that a racemic mixture was we will produce from this case 2 enantiomers. What's the 2 enantiomers? They're just simply, they have the same connectivity but different orientation in space now because of the X, okay, nga added. Okay, so you have reactions, you have 2 enantiomers occur at the same rate, and enantiomers are produced in equal amounts, so you actually produce a racemic mixture. So for example, one is an R, the other will be an S, and they are present in equal proportion, 50-50, and we call that one to be a racemic mixture. So an example, not an example. Here you have a propene and then propene. You have your, what is this? Is 1, 2, 3. So you have your butene here. Okay, you have your HX. Again, you're cutting a carbon, will add 2 hydrogen using the pi electrons. You get your H2H and you get your carbocation here. So you have a planar carbocation. Your halide can react to this up and below the plane. This is your achiral trigonal carbocation. So what you will get actually, you have your butene here rather, you will get your halobutane, okay? Wala na specify kung saan halide na here. So it will, if this adds up, you get this one, and this two will be pushed downwards. You have here to have our trigonal, our tetrahedral rather structure. And if this halide reacts sa ilalom, you get this one, and you have here an S and you have an R enantiomer. So the carbocation reacts with the halide ion at equal rates by path A or B. So you get 50% an S and 50% that is B. Okay, so what you get is a racemic mixture. So that ends our discussion, and we will continue with the addition of water next meeting. And you will have to upload another problem set, which is chapter 3, the one that I have mentioned. Okay, problem 83. Okay, that's all for today, and see you next meeting. And yes, do you have questions? I promise that we'll discuss. I promise that we'll discuss with your problems, or maybe we can discuss at other times. When do we discuss our problem? Maybe Wednesday? Is it okay with you? Can discuss your problem sets Wednesday na lang, ha? So, yes, do you have question? Or do you want na now na? Okay, rapod them. Or kapoy na ko. So, Wednesday na lang, ha?
Yes, ma'am.
Okay, so that ends our session, and see you next meeting.